Alrighty, let's see. Cool. So, we shall continue our... Good morning, Kevin. We will continue our, exploration of equilibrium today. Today's probably going to be a shorter class. I only have like 3 more examples to throw at you guys, and it's really just more of the same stuff. So, we'll just probably end a little early, which is okay. Tomorrow we will have our review session. Unless you guys want to do it on Thursday instead, it does not matter to me. I'm not going to throw new material at you. Just for one day doesn't seem really useful that way. So we can do it either day. Just let me know in Discord, I guess, if you prefer Wednesday or Thursday for our review. I did put up some practice exams for you guys. They're not from me, unfortunately. I could not find stuff on this particular computer from when I last taught the course, so I stole some from colleagues, I guess. They're up there. Just be aware that for those exams, they do cover slightly different topics or order of topics, so just focus on the ones that we've covered. So the first exam will have solutions as well as transition metal chemistry, so just ignore all the transition metal stuff for now. So just look at the solutions ones. The keys are also up there, so you can see all the answers in the process for that as well. So that's up there. So there's really one last thing that we didn't cover yesterday, which is one last bit of Le Chatelier's principle. Part 2, I guess we'll say. And that would be the introduction of things that don't matter into our equilibrium. So there are going to be several things that we can kind of throw in to an equilibrium that are not going to change anything, unless it's really a drastic thing. We saw that adding or removing pure solids and liquids is not really going to change anything in our equilibrium. So we talked about messing with concentrations of reactants or products. We do not care about solids and liquids in terms of concentration or activity because the concentration does not change for solids and liquids. They always have the same concentration because they are pure. We're going to assume that this adding or removing pure solids and stuff is not going to change the volume of a container of gas. By that, you technically could have an increase of pressure or decrease of pressure depending on what you're doing with the solids or liquids. So let's just not even get into that. Don't worry about that. So that's one thing we can deal with. We're going to see adding inert gases will also not change anything. So this will change the total pressure, but not the partial pressures. Partial pressures would stay the same. So we're going to see that adding an inert gas is also not going to change anything with our equilibrium. So we have basically ways of messing with our equilibrium that don't actually mess with it. So let's say we need, for some reason, to have the container have higher pressure for whatever reason. We could add some argon or helium or something to it to change the total pressure without messing with our partial pressures. And as a result, we're not going to mess with our equilibrium. And the last thing is adding a catalyst. So catalysts, as we studied last time, they change the mechanism of our reaction to allow it to happen more quickly at lower energies. However, just because we've defined equilibrium as when the rates of forward and reverse reaction are equal. Remember, catalysts just change the mechanism, so we still have forward and reverse reactions. So just making those happen faster does not actually change your concentrations. at equilibrium. So catalysts are not going to have any effect in terms of Le Chatelier's principle, just going to help things happen faster. But we're still going to end up with the same equilibrium whether or not we used our catalyst. So just putting that in there as well. So that's kind of the last bit of new information that we have there. So I think on the practice exams you'll have plenty of, and the homework as well, you'll have plenty of like, what happens if I do this, if I do this, if I do this. And so you can see those as well. I did change the homework to be due on Sunday the 14th, so you can spend your Valentine's Day instead working on those. The reason for that is the 15th is a holiday. I'm not going to give you guys an exam on a holiday. That would be just... maybe I should. No, that'd be just too mean, Enjoy your holiday. So we'll have your exam on Tuesday, as per the syllabus. So, cool. Alrighty, any questions on this sort of stuff? Before we do a couple of examples, I again just have kind of 3 examples here, and then we're done. So, yeah, short chapter. I like it. Unlike kinetics, which we took 2 weeks to do. Blah. All right, well, let's go ahead. And let's see, let's put KP down here. All right, so let's go ahead and say we started with these guys. So I think we've done plenty of ones with KC instead. We'll use KP this time. We're going to see it's exactly the same. Nothing's really going to change in this particular one. But we'll do another one where we start with PCl5 instead and see what happens there. So obviously in this scenario, we can see that Q is going to be definitely less than KP, right? We have 0 for our products. So as a result, the reaction proceeds forward. I mean, that's super obvious for us right now. But technically, at this point, now that we know how to use Q, you're going to want to technically evaluate it to see which direction your equilibrium is going to proceed. So let's go ahead and do it. So that means that we're going to be using up reactants, throwing in some products, plus 2. There we go, 0.43 minus X, 0.87 minus X, and of course X. So for this, we'll get 24.2. It's going to equal to X over 0.43 minus X, 0.87 minus X. Doing this stuff, do we really want to do it? I'll just give us the answers here. It helps when I do these in advance, so we don't have to deal with me fumbling around trying to solve a quadratic equation. But solve for x whatever way you like. These are the 2 options you get for x. So hopefully you can see that one of them is unreasonable. Right? If we look at our concentrations, we're starting with 0.43 and 0.87. If we subtract the first x, that's okay. We end up with positive numbers. But if we subtract the second x, we end up with negative pressures. Does not exist, so we can throw out that number. So we're going to find that x is 0.3955. So the pressure for the first one, for the PCl3, would be 0.43 minus this guy, which is going to be 0.0345, I hope. It's atmospheres. With sig figs, I guess we're just going to really end there, but we'll just keep it for now. That's of PCl3. For the other one, we had 0.87 minus that number. That's going to equal, oh gosh, this one I don't want to do in my head. 7 scare me. 0.87, oops. 0.87 minus 0.3955. So again, all this stuff is really the same, right? We're just doing a nice table. No real difference here. We're going to have that as our sig figs. That'll be our atmospheres of chlorine. And then, of course, our atmospheres of phosphorus pentachloride would just be X. Hooray! We did it. So hopefully nothing new here. If we really wanted, we could do the other way around. Let's say we had the same reaction. And this time we're going to just throw in 1.35 atmospheres of PCl5 and see what happens. This time starting with no reactants. If we wanted, we could flip the reaction around and then do the inverse of our Kp here. But why bother? We can just say, okay, we know we're going to use up some of the PCl5. We know that because Q is, in this case, going to be bigger, right? It's infinity. We have 1.35 over 0. So definitely Q is going to be way too big. So as a result, we're going to start using up our products. So we're going to add X to each side. A little bit easier math this time. So we know that 24.2 is going to equal 1.35 minus X over X squared. So we get 24.2 X squared plus X minus 1.35 equals 0. I actually didn't do this one for some reason, so let's do it now. Do your quadratic equation if you like, but I will cheat and use the internet. So what do we have? 24.2 X squared plus X minus 1.35 equals 0. What do we get? And the answers are rather, we have two options here, as always, because we have X squared, right? So we get 0.21643 and negative, 0.25775. Obviously, we can just get rid of this one. Definitely no need to have a negative X there. So we're left with the real X. So we can say that our pressure of PCl5, pressure of that, is going to equal to 1.35 minus X. 1.35 minus 0.216, let's say. We get 1.13 atmospheres, and the other two, I hate that there's two P's in a row. That'll just equal to X, which is 0.22 atmospheres, let's say. Hooray! Very exciting stuff. So, equilibrium works both ways. Start with reactants, you get more products. Start with products, you get more reactants. Easy. Very, very fun stuff. Questions on that one? Alrighty. Then let's do the other one. Alrighty, what reaction do I have this time? Okay. One of our favorite types of reactions. I don't know why these are so common, but here we go. Moving the oxygen around. Our favorite game in chemistry. Alright. 2 atmospheres for each one. 0 here. Alright, and I've given you a Kc this time. But I'm not going to give you a volume for our reaction. So remember, we can convert Kc into Kp. Hopefully we remember how to do that. Remembering that we have to multiply it by... Who remembers? So remember, we would take our Kc and multiply it by RT to the delta N power. I guess I should put the parentheses around that one instead. So, yeah. Did I write it wrong? Let's see. I think you've got it flipped, Kevin. Because I think Kp will be equal to Kc the other way. But now I'm second guessing myself. Kevin doesn't normally make mistakes. Oh no. Let's see. I could totally have written the wrong one. Let's see. Let me bust out the book here and see. But I believe it's Kc because the units, we're going to have concentration there. Concentration times RT. Let's see. Concentration is N over V. Yeah. Yeah, pressure should be nRT over V. Okay, cool. Alright. I can reason myself through this. Cool. Anyways, so let's go ahead and figure this out. So we're going to want to check what delta N is going to be. Delta N is the change of moles of gas from the products to reactants, right? So product, gas, moles, minus reactant, gas moles. Notice all of these, of course, are gases. So, in this case, delta N is going to be 2 minus 2 equals 0, which means Kp and Kc are the same thing. So, hooray. Yay, lucky us. We did all that work for nothing. Yep, exactly. So, all that work for nothing, but that's how we would do it if we had a different number of moles of gas on each side. So, let's do our ice table for this now. Now that we have our Kp, we can figure this out. Of course, given our kind of starting conditions here, we can tell we're obviously going to start forming products. But if we wanted, we could evaluate Q. We'd see Q is 0, which would be less than Kp. And that will tell us the direction of the reaction. So doing all this fun stuff, we get 11.8 equals x squared over 2 minus x squared. Thankfully, this is easier to solve than our previous ones because we can just take the square root of both sides. Now that we have everything squared on one side, we can say that rad 11.8 equals x over 2 minus x. Just square root both sides. Hooray. So whatever that number happens to be, let's do it. Square root of 11.8. All right, so 3.435 equals x over 2 minus x. Multiplying this guy by 2. So 6.87 minus 3.435x equals x. So let's just go ahead and make that 4. That'll equal 0. So 4.435x equals 6.87. X equals this number divided by 4.435. And I get 1.55 or so. Let's say 1.549, whatever. Same thing. Atmospheres. So that tells us that the pressure of our reactants will be 2 minus 1.55. I guess I should put our correct sig figs in there. And then for the products, 2 minus 1.55 it's just going to equal 1.55 atmospheres. So that's a little easier of a problem to do because we don't have to do any quadratics. We can just square root stuff and poof solve for x, and we'll have our answer. So, hooray. Alrighty, any questions on that one? Alright, then our last problem I have is a long one. So, I have it here. Ugh. On a textbook. This is not actually our textbook, but it has a good problem. I liked it. So we'll do it. So we're going to see kind of the use of some of this stuff in actual practice. So, we spent all this time talking about making ammonia, right? Most of which goes to farming purposes. But a fair bit, like about a sixth of it, goes actually to making nitric acid. So we're going to do kind of an exercise in making nitric acid here. So there's going to be two steps. This is called the Asphalt process, by the way, where we're going to take ammonia and burn it, combust it essentially, and we're going to make these guys. And step 2 would be taking 2NO, burning that further to make 2NO2. And then once we have the NO2, we're going to see how to make that into the nitric acid. Let's just do that now. Let's see, that's going to be 3 NO2s, yep, plus water will turn into nitric oxide plus 2 nitric acids, yeah. That would be aqueous. Okay, cool. So, couple of things to do here. So, the first one, it says, for step 1, so if we say air is 21% oxygen, and we should use 10 times as much air as ammonia should be used, we can figure out a couple of things. So let's see, what's the limiting reactant? And then from that, let's see what happens as a result of this. So, what the heck are we going to do with this? So, we are going to be using ammonia and oxygen here, right? We're burning together. And we're saying we're going to be using 10 times as much air as ammonia. And that air is 21% oxygen. So that tells us, we can say that, oxygen or air, one mole of air would have 0.21 moles of oxygen, right? And so if we want to compare here, saying we're using 10 times as much air as we're using ammonia, we know that we have 10 moles of air for every 1 mole of ammonia. Let's see if we can relate these two. It looks actually like we can use some nice conversion factor stuff here, which can give us kind of the ratio that we're looking for. So this is telling us that we are going to be using 2.1 moles of oxygen for every 1 mole of ammonia. How the heck does this tell us stuff about the limiting reactant? Let's think back to stoichiometry times. Well, let's look up at our reaction here. Uh, it's saying in our stoichiometric coefficients, we should be using 5 moles of oxygen for every 4 moles of ammonia. So let's evaluate that one. What is 5 moles of oxygen for 4 moles of ammonia? Let's go ahead and just reduce this. That's going to be 1.25 moles of oxygen for every 1 mole of ammonia. This is stoichiometry here. And this is going to be kind of the industry practice. So this tells us we use excess oxygen here. We only need 1.25 moles of oxygen for every mole of ammonia, but we're putting in 2.1 moles. So therefore, we're going to have excess oxygen here. And therefore, ammonia is limiting. And so let's evaluate kind of what's going to happen here as a result of this excess oxygen. So by using we can mess with the equilibrium. So let's take a look at what Kp would be for this sort of thing, or Kc, it doesn't really matter. If we go ahead and look at our reaction all the way up here, we're going to have 4 nitric oxides, 6 waters, 4 ammonias, and 5 oxygens. So, my gosh, that's so far up. NO times H2O, I think it was 4 and 6. It would be the pressures of these as well. We have, what is it, ammonia, and then oxygen, pressures thereof. By putting in excess oxygen instead of the amount that we would need, what effect is that going to have on our equilibrium? If we give it a little bit extra oxygen. What results is that going to have here? You can either, yeah, exactly. Not lower Kp, it would lower Q, right? So, because Q would be where it's not at equilibrium, whereas Kp is at equilibrium. So, I think you have the right idea. So Q will go down. So we're going to make more products. Yep, so that's going to help push this reaction further. So that's one way, in industry, how we can say, okay, we need more of the product here. We need more nitric oxide. How can we do that? Well, we have, ammonia, of course, is not something that's as easy to come by as oxygen, right? Oxygen we just have in the air. So if we can just shove more oxygen in here, we can force the equilibrium to produce more nitric oxide. All right, so that's a consequence of this Le Chatelier's principle idea, is that we can use this in real life, say, hey, we've got all this extra oxygen, let's just keep throwing it in there, forcing this equilibrium to make more products. And of course, that means more money and, capitalism, hooray. All right, that was part 1. Part 2, alrighty, we're going to be given a delta H for this. Delta H is going to be equal to negative 114 kilojoules per mole. So what's going to happen if we mess with the temperature? Or let's think about it this way. How should we adjust the temperature to make more products in step 2? So I'm just going to copy the equation because it's way up here. Okay. All right. Here is step 2 here. So what does the delta H tell us? Remember that the sign of delta H tells us that this reaction is going to be exothermic, right? Negative delta H means it's releasing heat. We're losing energy over the course of the reaction, so it's coming out as heat. And therefore that means heat is a product. So, if we wanted to make more product, we're going to want to lower our temperature. So, we would want to lower to produce more products. So that's what we would do in order to make this happen. So the third step is not really relevant, so we're just going to kind of skip it. But we can see here how in industrial chemistry, making very valuable components for reactions. Nitric acid is a super common reagent. We use it all the time. That these equilibria that these chemical reactions come across do have consequences that we can mess with. We can take advantage by knowing how to work with these equilibria in order to work them to our advantage. So we can see here that by throwing in extra air, we were able to make more products. And by lowering the temperature for the second step, again, we're able to make more products. So we're able to kind of take advantage of some of these facets of these reactions in order to make them work harder for us, as it were. So those are kind of the real life outcomes of learning about this stuff. So there we have it. Alrighty, so we are done with this chapter. Awesome, 15 is done. We are, a quarter of the way done with the semester now, something like that? Yeah. That's another exact example. So you can throw CO2 into a fire to put it out, right? So, while we don't typically think of fire as an equilibrium, that's definitely a good way to do it. So you definitely need minimum kind of concentrations there in order to react together. And so that totally is a good idea. So, yep, water would work as well. So, awesome. Alrighty, well, that's all I have for you guys for today. So, let's see. I'll just put this up in Discord as a poll, perhaps. Let's see. I'll throw in a new channel. And let me put a poll up here. So, review Wednesday. Let's have what emoji shall we use there? The happy toast, I think. And then review on Thursday instead. Let's do a how about a happy muffin instead? So you'll react with one of those. Let me put those up there for you guys. Where's the toast? Here it is. Okay. So alrighty, so you guys can vote, and we'll look at this. I guess I'll look at it later tonight, and we'll see it all, and I'll make the announcement what we're gonna do for that. It'll be just same time as normal, 10:15, and it would be an hour. How that works is you will also want to drop questions in Discord. So whether say, hey, can we do problem 2 from this exam or whatever, or hey, I really still didn't get homework question 84 or whatever. Whatever you guys come up with, I'm happy to go over. Just drop them there. Screenshots are good. Or if it's like from the practice exam, you can just throw the question number as well. So that'll work. So awesome. So yeah, I'll let you guys know what we'll do, and we'll see. So okay, yeah, we can say that. So the exam, how it's going to be done is, so it's free response. So it'll be very much like the practice exams that I've put up there. I'm going to be giving you 6 questions, so roughly 2 from each chapter, thereabouts. You'll answer 5 of them. So you'll pick 5 that you want to answer, and you will go ahead and do them. You will write on the exam or on a separate piece of paper, just depending if you have a printer. And you'll submit it on Canvas as a picture or PDF, just like as if it were homework. So it'll open up on Tuesday morning at midnight, 12 a.m. And it'll close at Tuesday at 11:59. So you technically have 23 hours, 59 minutes to work on it. But please don't take some time to sleep and do other stuff, like live your life, for sure. It should take approximately 75 minutes. That's what I'm shooting for. So kind of, at least allocate that much time for that. So, of course, it's open book, open whatever. If you're going to use Excel on that, I'll put instructions. Say if you used Excel, like write your equation for the graph or whatever, for if you're doing kinetic stuff. So that's how it's going to work. So yeah. What else was I going to say? Your homework keys will be put up on Sunday. They'll become available on Sunday so you can review them. Please do that. I'll probably be grading your solutions homework today. But remember, I'm not going to be giving feedback necessarily. So, I'll just be giving you a score. So the best thing to do is to look at the answer keys there and kind of just cross-check with what you've done to make sure that you're getting the right answers. And again, I'm happy to go over homework questions in our review as well. All right. So, and of course, if on Sunday when you look at the new answer keys and you say, wait a second, how the heck did this happen? Throw it out on Discord. I'll be happy to kind of walk you through it there instead. So, or Monday rather. I guess Monday is when the homework keys are coming out. So, alrighty. And of course, any other questions, throw them in Discord as well. We'll have that. So, there we go. All right. See you guys potentially tomorrow or Thursday. I'll let you know later tonight. I'll ping you guys in Discord what we're going to do. So, but yeah, I'll only be answering stuff that you guys write. So drop questions in there if you want me to go over them. So make sure you get on that. Just for anybody who's not as familiar, if we go to Discord, it's right here in our review questions. I've put a little thing here. That's where the voting is. You just click the emoji that you want to vote for. And then you'll also drop your questions there. So that's under C113. It's under there under review questions. So that's where that's located. All right. Cool. So see you guys. Enjoy your Tuesday.